Hello everyone, thank you for handing in your homework. Just thought I would use this to create a quick video going through the answers. So hopefully on the left hand side you can see the questions, and on the right hand side part of the mark scheme, and then the other part of the question I'll go through as well where people did have some problems with it. With the multiple choice questions, it can be quite easy to make silly mistakes, so it really is important to go through with a fine-tooth comb exactly what you need to do. Some of these multi-choice questions will take less than a minute because it should be seen as 1 mark per minute. Some will take slightly longer, but on average, if you have 20 questions, it should take roughly 20 minutes, but within that, some will take slightly more, some will take slightly less. So let's crack on with question 1. So Betelgeuse is a star in the constellation of Orion, which astronomers think could undergo a supernova explosion. What could Betelgeuse evolve into following the supernova stage? So given that it's a supernova explosion, you know that it's going to be a larger star, so the answer would be a neutron star. So it could have equally said black hole in theory as well. So the answer is B. For question 2, stars emit electromagnetic radiation. A graph of intensity against wavelength lambda for a main sequence star is shown. Which statement is correct as the main sequence star evolves into a red giant? Now you should know that a red giant will be cooler, and in chapter 19.7 stellar luminosity in figure 3 it shows that as the temperature goes down the peak wavelength moves to the right. In other words, the wavelength gets longer. So the answer for question 2 was D. For question 3, when the light from a star is passed through a diffraction grating, it forms a spectrum. Which of the following statements are correct? So, light emitted from the surface of a star would form a continuous spectrum. Light received from the sun has dark lines across the spectrum which correspond to the absorption of certain wavelengths by atoms in the Earth's atmosphere. A photon in an emission spectrum occurs when an electron moves from a low to a higher energy level within an atom. Now, this might well be a question that you need to spend slightly longer on. There's a lot of words, and I think from looking at the answers that I've got, a few people saw that they thought it might be an option, but they didn't read a couple of the key things. So if we look at the first one, light emitted from the surface of a star would form a continuous spectrum. Well, it would do. Absolutely. I know we've seen that there are black lines in this, or dark lines in this, links to question 2, but they are absorbed in the cooler part of the star, so in the photosphere in our sun, and this sneakily refers to the dark lines across its spectrum from the Earth's atmosphere, which it isn't, it's from the sun's atmosphere. And then a photon in an emission spectrum occurs when an electron moves from a high to a lower energy level, so not from a low to a high, so they'd swap that one round. So the answer for this one was only number 1, so for question 3 the answer was D. For question 4, what's the most likely evolution of a star which is 10 times more massive than our star? And I don't think there were any issues with this one. The answer was C. Question 5 caused a little bit of confusion. So the 4 energy levels of an atom are shown below. 4 electron transitions are shown by the arrows A, B, C and D. Which electron transition will give the longest wavelength of electromagnetic radiation? So, a few things to think about. Always, if you can, have an equation at the back of your head. So in this case, the one that always comes to mind is E equals HF. Apart from, we're talking about wavelength here, so the alternative is E equals HC over lambda. Therefore, energy and wavelength, so energy is proportional to 1 over the wavelength. In other words, if we've got the longest wavelength, it's going to be the smallest energy change, and the smallest energy change is A. In question 6, you had to draw the force acting on it. The vast majority, if you got that one spot on, The only thing I would say is just be careful. A few of you were a bit lackadaisical and did something like that, and of course you really need to make sure you're using a pencil and ruler and it's very clear that it's towards the sun. In question 7, a light source for an experiment is a discharge lamp containing excited atoms which emit several wavelengths. Figure 8.1 shows the 3 lowest energy levels of one of these atoms labelled N1, 2 and 3. Electron transitions between these energy levels can produce 3 different wavelengths of radiation. The transition between n equals 2 and n equals 1 causes 440 nanometer photons. Photons at 590 nanometers are also emitted, which transition causes these photons. Now this caused a little bit of confusion because a few people mentioned it goes from 3 to 1, but the answer was from 3 to 2. So let's just think about why that might be. So it's useful just to label things. So I've just added on here n equals 2 to 1, 440 nanometers. I can also see that the energy gap between 1 and 2 is larger than the energy gap between 2 and 3. So let's again, like earlier, look at our E equals HF. So then HC over lambda, and then energy is proportional to 1 over lambda. In other words, if you have a smaller energy gap, the wavelength will be larger. So the answer to this one has to be 590 is between n equals 3 and n equals 2. It couldn't have been n equals 3 all the way down to 1, because then the energy gap will be greater, so that would be going up, and then the wavelength of light given would be smaller than 440 nanometers. And then for the next bit, calculate the wavelength of the photons emitted by the third transition. So hopefully it's self-explanatory just over here, but in essence you had to appreciate that the energy from n equals 3 to n equals 1 is equal to the energy between 1 and 2 and 2 and 3, so that's what we've got just here. You then needed to convert that to hc over lambda, and then by doing that you can have 1 over 590, just because hc is a constant, plus 1 over 440, and then if you put the numbers in, and you could have used Planck's constant h, and you could have used the speed of light as numbers, but it's a constant so that you can use 1, and then you'd get 250 times 10 to the minus 9. A lot of you did times 10 to the minus 7, that's absolutely fine. Just these things tend to give an answer in nanometers rather than times 10 to the minus 7, but whatever comes out on your calculator, I'd strongly suggest putting in. With question 8, what's meant by a white dwarf? A lot of you mention this by maybe accident in a lot of cases, but what they're looking for is quite specific. So you needed to mention that it was the core and that it came from a red giant. A few people got confused and started talking about supergiants. Just be very clear that a white dwarf is from a medium or a low mass star, so one like our sun, and then after the planetary nebula, the core gets left behind from the red giant. For question 9, you really need to get into the habit of using data. So here we've got a series of data, and what you've got to do is analyse and evaluate it to show whether Wien displacement's law is obeyed. So the first thing is that you needed to show the examiner that you know what Wien's displacement law is. So you needed to state something like lambda max times t equals a constant for it to be obeyed. So you had to state that, and then you had to check to see if it was true. So you've got a temperature, you've got a lambda max, so you multiply the two numbers together, you'd write the numbers next to it, and you would see that they're pretty much the same. And if they are the same, which they are, you'd then state that it does obey Wien's law, and if they were different, then you'd say it doesn't obey, but because they were very similar, it does obey Wien's law. Now for part B, this was tricky. Calculate the luminosity of Untitled. Now probably the first thing you're thinking about is using that funny long equation, L equals 4 pi r sigma t to the power of 4. You didn't need to use that for this question. It was more of a logic question. You had to use that equation for the next part. So I'm just going to share with you my notes and then we will carry on looking. So the first thing that I did was try to visualize what the question was asking. So a sensor of cross-sectional area 4 times 10 to the minus 4. So that's this part here, that's my sensor. So it's mounted on a satellite and that's orbiting the Earth. And it's used to gather electromagnetic radiation from Untitled. And it's 550 light years away from Earth. So I've drawn a little arrow here. And then I just automatically converted it into meters because I'm convinced at some point I'll need to know how far away it is in meters. Now, when a few of you attempted this, you tried to work out the number of seconds, minutes, hours, days, etc. in a year. But what you really need to get into the habit of is use 9.5 times 10 to the 15 meters for the distance of 1 light year, and that is given to you in your data booklet. So it's in the back of your book. So the distance away multiplied together is 5.2 times 10 to the 18. I'm then given the radiant power, or power, entering the sensor, and that means that the power that's reaching this is the 2.6 times 10 to the minus 11 watts. And what we have to do is calculate the luminosity. So I've just written that to remind me just there. Now, first thing to consider is the intensity of light coming in, and we know that the intensity is power divided by area. So we know the power is 2.6 times 10 to the minus 11, and the area is 4 times 10 to the minus 4. So the intensity of light that's reaching it is 6.5 times 10 to the minus 8 watts per meter squared. Now, in addition to that, we've got a great big surface area of the light that's only partially reaching just here. So I've calculated the surface area of the star, or in this case I've just assumed it's a sphere. So I've done surface area is 4 pi r squared. Don't be confused, 4/3 pi r cubed is of course the volume of a sphere, so surface area 4 pi r squared. And then the final step is we want luminosity, and luminosity is in watts. And we've got an answer of power divided by area, so per meter squared. We've now got a meter squared. So if you multiply the two together, you remove the meter squared, leaving behind the unit of watts. So it was quite tricky. It wasn't straightforward at all. It was quite a logical structure that is only going to come with time, so that if you didn't quite understand it or get it, don't beat yourself up about it. More practice will come throughout the rest of the course. 4-part II, which looks like it's missed off on here, the radius. So that's when you did need to use the long equation, and it's a case of then using your value that you've put in from the previous part of the question, and then multiplying it by the constants, and then the temperature to the power of 4, which is sneakily in the table from the previous part of the question. And then finally, the mean density, calculate the gravitational field strength of Untitled. So you've got the equation G equals Gm over R squared. Then of course density equals mass over volume. So you're after the mass, so mass equals density times volume. You've got the density, and the volume is then 4/3 pi r cubed, and you'd calculated the radius in the previous part of the question, 5.8 times 10 to the 11. So it's a case of plugging the numbers in, and then the final answer is 7.1 times 10 to the minus 3. So I hope that's been useful, but any questions, please do get back to me.